Okay, sorry for the delay. So, welcome to live session 4. Yeah, okay. Thank you, Sindhu. I can see your message. Okay, so welcome to live session 4. And what we will do in this session, we will basically stick to the physics of welding mechanics. So, we will try to understand this analysis of heat flow. Just a minute. Yeah. So we will try to understand this analysis of heat flow and different kinds of models used to simulate the welding heat source. Also, we can see the analytical solutions of temperature distributions. People have already done that. We will see question by question. We will try to cover the aspects of this welding mechanics. Okay. So the first question is from this residual stress thing. Now, can anyone tell me what is means why residual stress generates during welding? Some raw idea. What is the residual stress? Anyone, please? What is uh, residual stress? Hmm? Okay. So if we want to define residual stress, so you can tell residual stresses are those stresses that remain in an object, right? So this is very particular in a welded component. So even in the absence of some external loading or some kind of thermal gradient, if you do some if you do some XLD analysis, I'm not sure that you are well aware of this XLD analysis or not. This is kind of a procedure through which you can uh, measure the residual stress in a structure. So residual stress basically result in a significant plastic deformation, which can lead to some kind of wrapping or distortion of an object, right? So residual stress is basically your internal stress, which remain in the object, right? Should remain in the structure. Now, I don't know you have seen or not. Let's say you are heating up a plate material. Let's say this is my top view of a surface. Okay. Now, let us assume that we are heating up this material. So this is a flame we are producing over this surface, and uh, we are moving it generates when one molten metal goes to solid state. Just a minute. You have typed that it generates when one molten metal goes to solid state, then it produces residual stress. Yes, means it's not obvious that you have to go to molten state, then it will generate residual stress. So Whenever you are heating up a material and then cooling it, because of something called thermal expansion coefficient, it generates over there every time. So yeah, let us assume that this is my flame which is traveling at a certain speed over this sheet surface, and if you are always heat and cool, there will be something called thermal fatigue will generate, and because of thermal fatigue you can see that the sheet will get bended, so it will form a curvature like this. Have you seen any time these kind of phenomena? You can hear of some process called laser forming. So laser forming is basically some kind of technique where you can basically form your metal surface through the heating and cooling method. Now, what is happening here? If you are heating a material, let us say this was my workpiece and this is my fusion region, okay, where I have melted the workpiece surface. Now, whenever you are heating a material, let us assume this is a bar element. This is a, I need to keep it small. Let us assume this is my bar element, okay? Uh, some kind of bar element where this is fixed over at one end, okay? Now I am heating up this material. I am heating up this material through some flame. It will try to expand, yes or no? So it will try to expand over here, wherever it is feeling free, right? So some kind of thermal stress will generate over there. Now, how can you define thermal stress in mathematical term? Can you define thermal stress in mathematical term? So let's say sigma thermal is what? This is E into alpha into delta T into this strain, where alpha is thermal expansion of coefficient, right? So whenever you are heating it up, it will try to expand at this free end, and in the vicinity of that free end, it will try to basically it will provide some opposite reaction force, right? Same thing is happening in the welding structure. Wherever you are doing this melting thing, there your structure is trying to expand over here. So it will feel this tensile stress over here. And in the vicinity of this, let's say this is my heat affected zone. In the vicinity of that fusion region, it will form some kind of compressive stress over there, right? And next, when you are cooling it, so this was during my heating, right? This was during heating. Now, when you are cooling it up, so it will try to shrink over here. Just try to shrink. And in the vicinity of that region, they will generate this tensile. So if over here this is compressive, over here this will form this tensile residual stress. And because of those tensile residual stresses, you can most of the time you can see those crack formation at a fusion region, and this bending happens over there, right? Any question? Why this? What is residual stress particularly? Now, how can you measure this residual stress? There are different kinds of techniques, of course. Now, there are this non-destructive techniques like XRD I mentioned. So, XRD is X-ray diffraction technique, right? Now, in X-ray diffraction, the maximum depth will be about some 0.05 mm. So, this is kind of a subsurface measurement that requires always some electrolytic polishing to remove the layers. Then there is something called neutron diffraction, where it can measure the residual stresses deep below the surface to depth of something around 30 centimeter. So neutron diffraction is very much accurate to measure this residual stress to a higher level of depth in a surface. Now these kind of diffraction techniques, basically which principle does it follow? Anyone? So it follows something called Bragg's law, right? You have already heard of this Bragg's law. Now, what is there in Bragg's law? This is lambda equal to 2d sine theta, is it not? So in Bragg's law, your theta is the scattering angle. This is scattering angle, right? What is d? D is interplanar distance, correct? And what is lambda? Lambda is the wavelength. Wavelength of what? Wavelength of the radiation, basically, particularly the radiation, right? Electromagnetic radiation. Now there are these semi-destructive, or there are techniques like fully destructive techniques, like you can drill some hole, or there is something called contour method, slitting section method. I'm not going into the methods per se, but the basic principle of this measurement of residual stress is the stress relief method. And these methods are used if the measurements are limited to only one point of the structure, which can be repaired very easily, right? So these methods are useful if measurement need to be done to single point, right? Now, how can you reduce these residual stresses, or what are different techniques to minimize, of course, the distortion also? So these residual stresses, distortion, these things are interconnected. So to reduce residual stress, you can always select the appropriate process and procedures, the sequence of welding, the fixturing of your structure. You can select the best method for relieve the stresses. You can select the design detail and materials so that you can minimize those effect of residual stresses. है ना? Now, how can you minimize the distortion? As I explained over here, how can you minimize the distortion? So the fixture plays a critical role over here. So welding fixtures that need to be take care of this distortion, which can restrain the parts, right? And there is something called tack welding. Have you heard of this term, tack welding? So I was talking about this tack welding. So tack welding is basically done at multiple points along joints to create a rigid structure. So this is done at multiple points along the joint to create a rigid structure prior to the seam welding. And you can always preheat the base metal part, preheating of base metal. Then you can do some stress relief heat treatment also. Those are few of the techniques through which you can reduce those residual stress and distortion over a structure. Okay, now based on the discussions, can you tell me which methods are not used to relieve residual stress from the weld part?
Option C, sir.
Option C. C is surface rolling. Yes. So this is not used to relieve residual stress. As I was saying, this stack welding can be used, then we can use this welding sequence. Are you familiar with this short pinning? What is short pinning? Anyone? So short pinning is basically we use this short pinning to improve the resistance to fatigue actually. So this is kind of a process which specifically designed to enhance that fatigue strength of components which are subject to some high alternating stress. Now, if you see the surface treatments like grinding, like milling, uh, bending also, those things causes this tensile residual stress, right? And this tensile residual stress leads to this low life cycle of the parts. Now, what short pinning do? Short pinning converts those tensile residual stress into compressive residual stress. That leads to a significant increase in the life cycle of the part and their maximum load capacity. Okay, so what I was talking converts tensile residual stress into compressive one. Any question? So if you see
Yes,
this short, anyone was asking any,
in short pinning, if a welded structure is suppose thickness is 10 or 20 is short pinning is sufficient for relieve the internal stresses for through thickness up to 10 or 20 because short
so
pinning is required for surface on the subsurface.
yes, mostly in lab, in research lab, we do it for this additive manufactured part, like when the struct you have like bulk amount of bulk volume of structure, and then you can basically short pin over the surface, and then you can uh, reduce those or convert those residual stress into compressive one. Now for small structure, as you were suggesting, for this 10 mm, 20 mm structures, for those things means I have never tried, so I should not comment over that. But excluding short pinning, we can always design. Means during the welding, we can design the thing in such a way that it can restrain those residual stresses. Uh,
Okay, okay, sir.
okay, so let's come to the question two. It says that which of the following equation represents the volumetric heat distribution at the center of the ellipsoid heat source model? So this is something on this modeling person. Anyone give it a try? What are different kinds of models of welding heat source you have come across? There is something on this circular heat source. You have this ellipsoid. What else? You have this double ellipsoid also. Then there is something called conical heat source. Also, there is something called adaptive heat source. So, depending on your temperature, you can adapt those Whirlpool size and safe. Now, if you are thinking in terms of yes, like the derivation, of course I will not go into the derivation of those things. Now, initially, in terms of this circular heat source, or you have this Gaussian heat source also. So, how will it look like? This Gaussian heat source. Let us first take this Gaussian heat source. So this will follow this Gaussian distribution simply, right? So if Q is my heat flux, which is a function of this radius, then let's say this is my Q max, the max value at some particular radius, right? So Q max R, which will follow exponential distribution, and this is something like this. So C is some coefficient based on which you can measure that how the distribution is spreaded over a location, right? Then you have this ellipsoid or double ellipsoid, which is a little bit complicated to model, but yes, there are some geometrical parameters which need to be initially identified, and then um, yeah, you have to identify those parameters for a particular model, for particular modeling. What are those geometrical parameters? So that's same. I'm trying to draw the schematic. I don't know how much I can be successful. So let's say this is my ellipse. Okay. So this is my ellipse, and this will be in the depth. This is towards depth, and let's say this is the axis. So this is my x-axis, and so this is my y-axis, and this is my z. Okay. So what are the parameters here over here? Why I'm getting oh, yeah. So this is, let's say, A. This is my B, and let's say this is something like this. So this will basically follow some non-uniform distribution at the front end and the rear end. So if you're thinking of this melting or depositing a melt over a surface, so at the front end of the heat flux, uh, it will follow some distribution which is different from its rear end, right? So that's why it is two different parameters, CF and CR, right? Now, what is Q at front end, which is a function of this X, Y, Z, and T? So this will be some term uh, which will be which will be a function of, let's say, I don't know, this, there will be this eta, so the efficiency is there, this is total heat flux is there, then there are some coefficient called FF at the front end. So these are kind of empirical formula. So this is specific to your specific experiments. Depending on your process parameters, your whirlpool weld size, those things can change, right? And depending on your experimental values, you need to somehow empirically uh, do some sensitivity analysis and find out those A, B, CF, CR, FF, AR, those values. So these are some empirical equation. Now, this is a function of A and B also. So there will be some term like this 6 root 3 f. eta into Q by A into B into CF into, there was some term I forgot, in terms of pi, and then that into, you have this exponential of, this is a elliptical thing, right? So you have this, for 3D, you have this minus 3x squared by a square into e to the power minus 3y squared by b square to e to the power minus 3z squared by c square. So for QF, if you want to find out what is the heat flux at front end, you can keep it here, the CF value. If you are trying to find out the value of QR, this is CR. That's how it works, right? Now, this is kind of non-symmetry in energy distribution because of this moving heat source, and yeah, at the front and at the rear end, it will behave differently, right? Hmm. Now, what it says, what does it ask? Which of the following equation represents the volumetric heat distribution at the center of the ellipsoidal heat source model? What will be the distribution at the center? So this was the 6 root 3 f eta q ABC into root pi. That into this. Now at the center, can you tell me what will happen? So basically you need to find out q at 0, 0, 0. Anyone? What will happen at q at 0, 0, 0 if this q x y z is 6 root 3 f eta q by, I have already just, you just put x, y, z value at as 0 and then tell me the answer. What will happen? You put x equal to 0, this will be e to the power 0, 1, y equal to 0, 1, z equal to 0, 1. What is the correct answer then? Option B. Are you getting it? Or is there any confusion? Mm-hmm.
Not understand, sir.
So, my equation was simply, let's say q was 6 root 3 f into eta into q, that divided by a, b, c root pi into e to the power minus 3x square by a square to e to the power minus 3y square by b square to, this is a generalized equation of an elliptical heat source. If you don't remember, I'm writing it down over here. So this is a generalized term of an elliptical heat source. So, so Now I'm asking over here that uh, the volumetric heat distribution at the center of the ellipsoidal heat source model. So at the center in the sense, let's say x equal to 0, y equal to 0, z equal to 0. So if you are putting x, y, z as 0 over here, what will be this? So it will be simply 1, है ना? So it's all e to the power 0. Got it?
Okay, sir.
Now, uh, now there is something called adaptive heat source model. So this adaptive heat source model, during the simulation or during this modeling, what we do is like, let's say this was my well structure over here. Again, give me some time to this draw the schematic. Now let's say you have this kind of structure. So this is my weld metal over which I am providing this heat flux like this. Okay. Now let's say my weld pool is something like this. So this is my weld pool size. Um, just over which this is the depth. Okay. So if you are thinking of this cross section, this will be seeming like this. This is my pool depth. Okay. Now let us assume that this is my center of the heat source. Okay. So this is my center of the heat source. Right. Now what are there? You have this. One is this. One is this at the front end, at the rear end. Then you have the depth term. It says C, and then you have this thing B, right? I'm drawing it in 2D levels. So initially, when I was drawing that double ellipsoidal hexes, that was drawn in 3D. Now it is in 2D. So this is my B, correct? Now in the adaptive heat source model, what we do, this this was my CF and CR, you know. So we keep the total C as CF plus CL, which will be the melt pool length. So we do the experiment and then we measure from scanning electron microscope how much the melt pool length is coming, how much the width is coming, how much the pool depth is coming, and after that, you can basically put those values into your model and then simulate the complete process. Okay? So B is this Wi by 2, where Wi my melt pool width, and this, sorry, this is something else. So basically, I wrote both the things as C, that's why I removed that. So let's say this is D. So what is D? D is on melt pool depth. That's how this adaptive source model works, right? And in the simulation, what happened? These values, this length, width, and depth, those things change with ramped up load. So this LW and let us say T is my depth, can change with ramp up load. And the model can adapt itself with changes, right? So it can convert the values of those LW and T in a load step and then do some iterative calculation to find out the final value over there. So that is something on this finite element simulation. Let us not go into that detail. But yeah, that's how it works. Okay. Okay. So let's move to the next question. This is from analytical solution of this temperature distribution. And that is something on Rosenthal's steady equation. Do you remember this Rosen? First tell me. First tell me. Uh, just we will stick to the basic. There are a lot of analytical solution, of course. Uh, I I can understand it is not possible to remember each and every equation over there, but just stick to the basic. Um, just tell me, are you familiar with thermocouple? What is thermocouple? Anyone?
Yes, sir.
What is thermocouple?
It is nothing but temperature sensing element,
So
which
through thermocouple, you
like
can measure the temperature over a specific location at different point of time. So through
yes, yes,
thermocouple, you can record uh, a temperature evolution
yes,
basically,
yes.
है ना? So let's say I have a top sheet over here. Top sheet in this is the top view of the sheet metal. Okay, this is my top view. Okay, and this is my y-axis. This is my x-axis. Okay, and this is the center line of the surface, top surface. So this is y equal to 0. So this is my longitudinal direction, and this is the transverse plane. Okay. Now my thermocouples, let's say my thermocouples are connected like this. So these are my three thermocouples we have connected through some data acquisition system. So I'm using some data acquisition system and see the how the temperature evolves over time. Okay. Now let us say I'm moving a flame through the center line like this in this direction. So VMM per second. So how the temperature will look like? So this will basically, let's say for one location, this is my spot one, this is spot two, this is spot two. So how will it look like? For spot one, this will, when the flame will reach over spot one, this will feel the peak temperature will reach. And then when the flame passes by, it will start cooling like this. Agreed? Yes or no? Anyone please? Yes or no? It will be
Yes,
simply
yes.
heating and cooling, right? So this is my spot one. How it will behave for spot 2 and spot 3? It will follow same kind of distribution. Of course, the distribution will be same. Like in terms of peak temperature, it will be same or something uh, on higher side or something on lower side. What do you think? For spot 2 and spot 3, as it goes from spot 1 to spot 2, what will happen for spot 2? Ideally to say, will the peak temperature be same what spot 1 is feeling or it will be somewhat different?
temperature gradient will decreases.
Sorry,
Temperature will be decreases. The temperature gradient.
temperature will be decreasing. Why? Because this is in the same plane. This is in the same plane. I'm not talking about the transverse plane away from this center line. So the temperature would decrease if the thermocouples were connected like this. So if you are familiar with this temperature contour term, so and also this how this contour will look like this. So at the center it will be matched. So this will be, let's say, the red, and here it will be green, and then it will be blue like this. So away from the central line in the transverse direction, yes, the temperature will be less, but in the same plane, ideally you will see that spot 2 and spot 3 all will experience the same kind of peak temperature, but yes, of course, after some point of time, depending on this heat dissipation property of the material, why this will follow the same peak temperature. So if we somehow add this peak temperature, let's say I'm adding those peak temperatures. So this is something like after some time, this is coming at a steady state. Is it not? Now, why this is coming at a steady state? This is simply because of energy conservation, right? Now, what energy conservation tells you? The energy conservation tells me whatever heat coming in, that much of heat will get accumulated. What does that mean? Are you familiar with this Fourier heat law conduction? I hope you are familiar with, everyone is familiar with this Fourier heat law conduction, right? So Q is equal to minus K dt dx. You're familiar with this equation. Tell me this is 1D or 2D or 3D, this equation. What is the type of this equation, 1D or 2D or 3D? 1D, right? So this is a 1D equation. Now, how does it look like in 3D? So we call it divergence. There is some theorem called green divergence theorem. Let's not go into that depth. So again, so in 3D, it will be something like del x of kx gdx plus del y of ky gdy, and then del of that term. And then this is due to conduction of the metal workpiece. That minus you can consider the convection heat loss, which is H del T, and then you can consider the radiation heat loss, right, which is proportional to the fourth power of that temperature, right? So those convection and radiation heat loss you can consider, that will be equal to, what is that? Heat getting accumulated. So mCp dt dt, right? That is my governing equation of any kind of heat transfer solution. Yes or no? What is Cp? What is Cp? What is CP? Have you heard of this term specific heat? Yeah. Yes. Okay. Yeah. So CP is specific heat. Right. Now, now can you tell me, let us take two different cases. Let us take two different cases. What are those cases? Um, let's say I'm heating a copper material which is having high thermal conductivity, and I am heating a steel material which is having somewhat lower, of course, very much lower uh, conductivity compared to copper. Okay. Now, for one case, I'm drawing my temperature contour plot. Okay. So this is one of my temperature contour, and this is another temperature contour. Now, can you tell me which one will be for copper and which one will be for steel? First, take this one. This one will be for copper or this one will be for steel? The the heat affected zone is very wide, and yes, is this for copper? No, this will be for steel material. So copper can dissipate heat very quickly, so it can cool up very easily. That's why it will be having less heat affected zone. So for copper, you will see some kind of elongated structure. Okay. Now, can you tell me if this is, let's say, this elongated contour will be for copper and white contour will be for steel because of its heat dissipation property. Which one will be for higher welding speed and which one will be for lower welding speed? So if you are doing some welding with very high welding speed, the temperature will be very less, right? You are not giving enough time to rise the temperature to certain extent. And if the temperature is not going to that high, it can cool very easily. Now tell me which one will be for higher welding speed. You can use chat box. Anyone replied?
Please repeat the question.
Sorry.
Repeat the question, sir.
So let's say this is an elongated contour and this is a wide contour, temperature contour. So my elongated contour will be following this higher welding speed or lower welding speed.
Higher
So
welding
yes,
speed.
this is for higher welding speed. Exactly. This is for higher welding speed, and this will be for lower welding speed. You got it, right? Now, coming to this equation, coming to this question, um, let me write this Rosenthal's 3D equation, and then we can solve this question. So, it tells me, Which of the following is correct with respect to this Rosenthal steady equation? Now let me write this Rosenthal steady equation. So this is temperature gradient delta d del x, that will be equal to minus 2 pi k T minus T naught whole square, that divided by Q. Now tell me, it says that temperature gradient increases with an increase in the temperature difference. Next, the temperature gradient decreases with increase in the temperature difference. Then it says temperature gradient increases with an increase in heat input, or it decreases with an increase in heat input. So Q is my heat input, K is the thermal conductivity. So here you can see directly the temperature gradient is directly proportional to the square of the temperature difference, है ना? Which means that it will increase with an increase in the temperature difference. This is true. And then the temperature gradient is inversely proportional to the heat input, right? If Q is the heat input, this is inversely proportional to the heat input. So the temperature gradient decreases with an increase in heat input. This one is true. So 1 and 4 is correct. Any question? Hmm. Okay, good. So let's move to the next question. I would say this question is little bit tricky, but not like it's a very simple question. Just go through the question once. There are a lot of informations provided here. So you have your voltage, you have your current, you have your for your elliptical heat source, you have your Happoid depth, then you have your heat fraction for front and rear, right? Then you have to find out or calculate the front and rear quadrants heat flux ratio of the moving heat source. So what was there for this double ellipsoidal heat source? So if it was QF, which is a function of R, that was 6 root 3 FF eta Q by AF B C pi root pi, that into uh, e to the power minus 3x square into e to the power minus 3y square by b square, e to the power minus 3z square by cf square, right? And for QRR, this all will be this AR, CR, here also it is a CR. Now you need to calculate the front and rear quadrants heat flux ratio at the center of the ellipsoid. As I mentioned over there, X, Y, Z all is equal to 0. Now tell me what will be the ratio. Just let me draw for your understanding once. Oh, sorry. I'm not talking about this B, C, and those things. Anyone trying? So what will be QF if X, Y, and Z equal to 0? So this will be simply 1, right? So QF of R, again, this is will it be a function of R? Yes. So 6 root 3 FF eta Q AF BC pi root pi. Got it? At the center of the ellipsoid, what will be QR 6 root 3 FR eta Q AR BC pi root pi. Now tell me what is the ratio of QF by QR? My QF by QR will be heat input fraction. Am I doing something wrong? Ah, sorry. So this is 0.4 by 1.6 into. So rear semi-axis is 16 AR, 16 by 4. Tell me, do you have any question? How much is this coming? Zero point 0.4 by 1.6. This is coming 1, right? And if you got same answer or anyone have any other opinion? Tell me if not understood, or else I'll move to the next question. Okay, so let's move to let's move to next question then. Which of the following statements is or are correct? Preheating the base parts minimize distortion. The cooling rate does not affect the microstructure of rounded parts. The cooling rate affects the microstructure of the rounded parts. This is very simple. Can you give me the correct answer? I told that preheating the base part minimize distortion. That is true. Cooling rate, of course, affects the microstructure of the welded part. That is also true. 1 and 3. Yeah, D is correct. Neutron diffraction is not a destructive technique. So, in terms of distortion, what are different kinds of distortion you have heard of? So, there is this, this longitudinal shrinkage, then there can be this transverse shrinkage, you can have angular change, then you can have this bending, buckling, many kind of distortion effects are there. Now, how can you eliminate distortion? Yeah, D is correct. You are right. So, how can you eliminate distortion? So, to eliminate distortion, you can do something like prepare some preset members which can counteract the distortion, which can counteract the distortion, right? So, if your structure is like this, you can prepare your structure like this so that this kind of negative the effect, right? And then you can use the fixtures to clamp the workpiece in place. So the fixtures will basically restrain or reduce the distortion, but it can increase the residual stress. That you have to keep in mind. And as I mentioned that you can do some stress relief treatment, right? Now, if you're thinking of different kinds of factors which affect the distortion, so yes, in case of this uniformly heating and cooling, if you are uniformly heating and cooling one structure, the distortion would be minimal compared to non-uniform heating and cooling, right? Now, yeah. So welding, what welding do is welding locally heats a component, right? And the adjacent cold metal restrains that sheeted material, as I was explaining during that. Why there will be that buckling or bending due to that heating and cooling over there. So it's all because of those tensile and compressive residual stress concept. So yeah, we have uh, we have done this question 5 also. Hmm. This is also a very small kind of question. You have your cooling rate which has been estimated as 100 Kelvin per second, and you have your solidification growth rate 8 per second. What do you need to find out? The average temperature gradient. So you have your solidification rate. So we signify it in terms of R. And then you have your temperature change. Call it G, right? Now what will be the cooling rate over here? How can we define cooling rate? Cooling rate is basically your solidification rate into the temperature gradient. Okay, how your solidification rate is defined? So Tt by Tt. So if you have like so this is my y-axis, this is my z-axis, and then you have some structure like this. So this is at 0 degree my T and this is at 90 degree my T, and this is my mushy zone. Mushy zone in the sense both liquid and solid coexist, right? This is my mushy zone, and this is liquid. So how your solidification rate is defined? This is the differentiation of that D average, and your G average will be temperature gradient will be T max minus the solidus temperature that divided by E. So let us concentrate on this thing. The cooling rate will be solidification rate into temperature gradient. Just give me a number. Mhm. How much this is coming? 1000 K per second, 1000 Kelvin per second, which is my cooling rate. That is equal to solidification rate into temperature gradient. So much this is coming? 100 by 8 is 25. Okay. Okay. Again, I have already discussed which of the following residual stress measurement techniques follow the basic principles of Bragg's law. Hmm? Basically, the non-destructive techniques, right? X-ray and neutron. These are semi-destructive or destructive. Okay. So moving to the next numerical. So in this numerical, what does it tell? In an arc welding process, you have your voltage and current, which is 26 volt and 230 ampere. We need to calculate the heat input per unit length. In my earlier videos, I have discussed in terms of what is heat input per unit length. And then The arc transfer efficiency is provided and welding speed is provided. You need to calculate heat input per unit length. What is heat input per unit length? That is defined as Q by V. My total heat flux which is coming in, that divided by the welding speed. Now what is total heat flux which is coming in? You have your voltage, you have your current, you have your arc transfer efficiency. That divided by welding speed. All values are provided. 0.85 into 26 into 30. 5. How much is this coming? There are some unit conversion I need to do. Mhm. No, it's fine. We need to calculate it in terms of joule per mm. So this is in mm and this will be in joule. Yeah. How much is this coming? Can anyone calculate please and give me a number? How much?
One zero one six six zero. 101660.
So this is coming. So I can
One,
consider this, right? 1017. Someone in chat box also missed. Um, this is 1017. Yes. Navnat. So this is coming as 1017 joule per mm. Everyone got it? So that's how you calculate heat input per unit length, right? Okay. Moving to next question. You have your butt joint, which is made of using an arc welding process at some specific current, at some specific voltage. Then you have your wear for diameter of some specific diameter, which is fed at a feed rate of some specific velocity. Then your density, specific heat, melting temperature, those things are provided. Then ambient temperature is also given. And it is mentioned over here that you can neglect the latent heat of fusion effect, and we need to calculate the total amount of heat that is conducted to the surrounding for a thermal efficiency of zero point 0.9. So, what is happening over there? You have some dia, which is 1.2 mm. My density is provided as 70 kg per mm. And my CP is 1000 Kelvin. And my TM is, sorry. So TM is 1435 accuracy. Okay. And ambient temperature is divided over here, 25 degrees C, right? So what will be my total heat input? Q, VI. How much is this coming? It's going to step by step. So you have your thermal efficiency as 0.9, right? That into 140 into 20. How much watt is this coming?
Sir, 2520 watt.
2520 watt. Okay, I'm not calculating it. So 25, let's assume that this is correct. 2520 watt, I am getting my net energy for heating the workpiece. Then how much amount of heat will be required to melt the world metal? So let's just mentioning it as Q1. Yeah. So it will be like you can think it of like this. So you have your velocity, right? You have your area of melt, right? So mild steel wire of a diameter 1.2 mm is fed. So you can calculate the area from there. So area into velocity, that is giving me the volume per second, right? And yeah, that into density, rho into volume, that is m into Cp, that into Tm minus T ambient, right? So I'm considering a steady state over here. So there is no temperature difference over time. So you have your velocity, which is how much? 138 mm per second, which is let's say 0.138 meter per second. Uh, do you need to, okay, as this is in watt, let's stick to SI unit. So 0.138 meter per second. Then you have this area, pi by 4 into d square, right? Then I have my density 7800 kg per meter cube. Then I have my specific heat, that is also in SI unit 1000, and that into 1435 minus 25, 1410. How much is this coming? How much?
Sir, 1716.5.
1716.5. Everyone agreed?
Watt.
Huh, this isn't what. So what you need to calculate? You need to calculate the total amount of heat getting conducted to the surrounding, right? So you have your net energy for heating the workpiece. If you have your amount of heat that is required to melt the weld metal, so how much is going into the surrounding? It's 2520 minus, that is basically your heat loss due to convection, radiation, whatever. So how much is this coming?
Sir, 803.5.
80,
3.5.
803.5. All good? Anyone have any question? Okay, let's move to the last question. The last question, what it says, we have our welding current, we have our welding voltage, then the thermal conductivity of the material is provided, transfer efficiency is provided, heat source is moving along x direction with a velocity of certain speed. You need to calculate the cooling rate. For the final temperature of 630, so you have your final temperature, you need to calculate the cooling rate. So I mentioned that equation, do you remember that, for Rosenthal's 3D?